In this video, we're going to continue our discussion of the Grignard reagent, starting to get into some practice of predicting products as we think about what we know about the mechanism and that sort of thing. So let's remind ourselves what's going on here. So the Grignard reaction forms a C-C bond and makes an alcohol. Okay, those are big deals. Alcohol is an important functional group. Carbon-carbon bonds are the most important bonds that we can form. All right, the reaction uses a Grignard reagent. Now, the Grignard reagent is generally drawn as RMGX, where X is the halogen that was once part of our haloalkane. Magnesium is now a magnesium plus 2. It started off as magnesium 0, and then the carbon, which is the big thing, is sort of like an anion. I'm going to cross out magnesium because it's just another metal. It's kind of like lithium and sodium. It does have more covalent bond characters, so this isn't totally accurate what I'm doing, but it does describe the behavior and the reactivity. Now, if I cross that out, I get my R minus, and we just assume that the magnesium sort of dissociated. It kind of doesn't, but if we do that, we can see that we have an R minus. This is a carbanion. What I want us to do is take a step back and recognize that this negatively charged species looks a lot like a nucleophile, and that's in fact exactly what it is. So it is a good nucleophile, and it's a strong base. And I'll just mention something quickly about its basicity. So let's go down here and just bring this down. So Grignard reagents are strong bases. Okay, that is to say that if you have R minus and you react it with some H plus, you will get RH, which is really just an alkane. If you get an alkane, then the reaction is dead. There's no Grignard reaction because we need that R minus. Now, that's an issue because when I say Grignard reagents are strong bases, I should clarify they are very strong bases. They can grab H plus from really any acidic hydrogen source. So if you have water or alcohol present, they will react and form things that you don't want. So they will react with alcohols and water, and I should clarify that when they react, it's generally been productive in this class, but this is not a productive reaction for us. This just forms some new alkoxide or hydroxide ion that we then have to deal with. So a bad, and I'm just going to emphasize a bad reaction, because this is just not a productive way to use your Grignard reagents, is if you have RMGX plus H2O or an alcohol, what you get, and I'm going to make the R, I'm just going to put like a prime just so we can separate this R from this R. Okay. Anyway, if we let if we put water or alcohol in the presence of our Grignard reagent, something unproductive is going to happen. You're going to form RH, which is just an alkane. Alkanes, they don't do anything fun, right? We have to do free radical halogenation to get them to a haloalkane that's remotely, that is highly useful, I guess, in that case. But alkanes are not that useful for us. The reaction is dead. We form hydroxide or alkoxide, but it's not the alkoxide that we wanted. And so if we quench this with our mild acid, we might just see ORH, get like ethanol out. And this isn't, the Grignard reaction is not the way you want to make ethanol. You want to make complicated alcohols, structurally complex alcohols, things that are otherwise useful that you can't just get by fermenting bacteria or yeast, excuse me. Okay, so this is an acid-base reaction. If you want to look at the curly arrows, what you do is first consider this RMGX as R minus, and then it's reacting with the acidic hydrogens that are attached to O. I'll just have O attached to anything. So these are acidic hydrogens. Now they're not H plus from like HCl. This is a much weaker acid, the alcohol in water is, but Grignard reagents are such a strong base that they can pull the hydrogen off of these things very easily. So we have to be careful about the solvents that we choose. So instead, we use dry, alcohol-free diethyl ether. And that's the one I'm going to put on the exams, right? For the predict the products, I'll use diethyl ether. These days, it's a little bit more convenient to use THF analogs. Plus, no, or THF. You don't have to worry about THF too much, and I'll try to stick to that. But THF is just a cyclic form of diethyl ether. It's a little bit easier to come by. Anyway, so that's an issue with Grignard reagents. But I want to get back to this again. So Grignard reagents are nucleophiles. Grignard reagents are nucleophiles. Now, in addition to that, carbonyls are electrophiles. And our carbonyl, again, is acetone. These are electrophiles. So just like the SN2 and really the SN1 reaction, remember I said that like a huge number of organic reactions are just combinations of nucleophiles and electrophiles. That's exactly what the Grignard reaction is. So the Grignard reaction is just the combination of nucleophiles, which is RMGX, our Grignard reagent, and electrophiles, which are the carbonyls. And again, I just can't emphasize it enough how interesting it was to me, at least when I was a student, that we take a haloalkane, that we just had this big unit about how the haloalkane is itself a good electrophile. But we convert it into a good nucleophile using the Grignard, using a magnesium metal atom to kind of do an oxidative addition into the haloalkane to form the equivalent of R minus, the equivalent of a carbanion. Again, it's just one of my favorite parts of this reaction. I said I would do some practice for the Grignard reaction. I think it makes sense to do that in a separate video. So I'm going to stop this video. And again, this is just, I guess, kind of a perspective video, some good insight as to why we need to be careful about the solvent and be aware of how basic Grignard reagents are. But otherwise, we'll practice this reaction in the next video.